Hello, my name is Mallory Chase, and we are the Satellite Warriors.
Hi, my name is Sabrina Boyle.
Hi, my name is Connor Jason.
Hi, my name is Kevin John.
Hi, my name is Darlubin.
My name is Charlie Cairns.
Hi, my name is James Overholt.
Hi, my name is Luke Venable.
Hi, my name is Kaylee Service.
Hi everyone, my name is Jamie Sims.
The following consists of our SMART goals. For communications, we need to use Bluetooth to send and receive commands effectively to transmit data between the CubeSat and the ground station at the rate of 1 image per pass. Altitude determination and control systems. Be able to calibrate the CubeSat IMU such that the CubeSat can detect the altitude with 95% accuracy and use it to determine whether or not to take photos. For power, we need to calculate the power of components, assuming that the power generated from the solar panel is around 1.4 watts. For structures, we need to keep the mass of the CubeSat within the mass budget and assemble the CubeSat structure properly to allow it to function. For imaging, we need to create a program that can only take photos from the Pi camera while facing the Earth and while it is above the ocean. Flight software. Design a software program that can interpret inputs of power and images. We need to process them and output necessary data to the ground system and other subsystems. For thermal, we need to ensure that the Raspberry Pi temperature can be consistently monitored and maintained to remain within an operable range between -40 degrees Celsius to about 85 degrees Celsius. And this is all due on May 7th.
This is a basic glimpse into our concept of operations. Our CubeSat will orbit at about 400 kilometers. Our mission is to find plastic in the ocean by taking and analyzing photos from space, allowing other people to better clean up the plastic that is destroying our oceans. The CubeSat has 3 main functions to achieve this goal: taking pictures of the ocean, scanning the images for plastic, and then sending the locations of the plastic to the signal receiver. In order to do this, we also need to be able to actually fly the CubeSat around space, including keeping control of the thermal subsystem and controlling where the CubeSat is facing.
This is a block diagram of how our CubeSat subsystems work together in the satellite. We'll look at the subsystems and their components, starting with the structure subsystem. The structure subsystem includes the exterior frame and its parts, including the base panels, acrylic side panels, acrylic side brackets, and the aluminum corner rails, which constitute the frame of the CubeSat. The solar panel from the power subsystem is mounted to one of the base panels, supplying power to the electric power system, which distributes the power to be either used by the Raspberry Pi or stored in the power bank for later use. The command and data handling system contains the processor for this CubeSat, a Raspberry Pi, which enacts all of the flight and image processing scripts, taking into account the CubeSat's attitude found using the Attitude Determination and Control Systems, or ADCS for short. In the communications subsystem, the CubeSat uses the Bluetooth from the Raspberry Pi to communicate with the ground station to send and receive commands, as well as to send the processed images taken back to the ground station. The thermal subsystem uses a temperature sensor to detect the temperature, and the imaging subsystem contains the Raspberry Pi Noir camera, which can be used to take photos of the Earth.
We constructed our CAD model in accordance with the way that we were going to build the structural components of the CubeSat. However, we started our CAD model by sketching and extruding the aluminum corner rails first, instead of doing the same for the acrylic side panels and the acrylic side brackets before fixing them together. This helped us to fit the side panels and the side brackets to the aluminum corner rails easily without having to rotate the corner rails around to fit the design. After adding the Raspberry Pi 4 Model B drawing to the CAD document, we used different mates to fix the CubeSat structure to the Raspberry Pi structure. All dimensions were made to match the exact dimensions of the real CubeSat. With regard to our structural and thermal analysis, our structural analysis will test the CubeSat CAD model under a variety of pressures through experimenting with different pressures or keeping a standard amount of pressure and forming a CAD model and structure that meet the pressure requirements and the mass budget of 1.33 kilograms for the CubeSat. Our thermal analysis aims to evaluate the CAD model with a steady state and transient model to see how our components deal with heat when it dissipates from one source to the entire structure, and also to see how the temperatures of the CubeSat vary over time and in orbit. Based on the structural component's attributes, heat will be conducted through the satellite in different ways, and the results of such models and experimentation will help us to optimize the satellite's method of dealing with the flow of thermal energy.
Here we have our total mass budget. In it we can see the various components of the CubeSat broken down, and each of their masses is displayed.
For power budget, our powered components were the IMU, the solar panel, the Raspberry Pi 4 Model B, the battery, and the camera. For charge rates, we calculate the expected power harvest of the solar panel by simply taking the area of the solar panel times the solar irradiance at the given location where the experiment or test is being done times the solar panel efficiency. The area of the solar panel that we are using is 0.002025 meters squared. The solar irradiance at ground level is around 1,000 watts per meter squared, and the solar panel's efficiency is estimated to be about 10%. At the end of these calculations, which I'd mentioned earlier, we get a figure of 0.2025 watts produced by the solar panel in 1 hour. For the expected power harvest in space, the solar irradiance would be the only factor that changes, where the solar irradiance is 1,361 watts per meter squared. At the end of the calculations that were mentioned previously, the watts that were produced by the solar panel would be 0.2756 watts. For discharge rate, we expect that the discharge rate of power from the battery would be around 5 volts an hour. General figures for Raspberry Pi 4 Model B power consumption include the Raspberry Pi in its different states and their respective power consumptions. So for example, in idle mode, the Raspberry Pi will consume around 2.7 watts in an hour. When it retrieves information in its uncached form from the main memory, it is expected to consume 5.1 watts in an hour. When it is at 400% CPU load, it is expected to consume 6.4 watts in an hour. Since we did not use any propulsion systems in this CubeSat, we do not account for such things in our power budget. The ADCS subsystem, which is found in the IMU, has a power consumption of essentially 0. This is because the power consumption of the IMU is of such low orders of magnitude that it can be considered negligible. The payload or camera's power consumption is around, or expected to be around, 0.4 watts to 1.4 watts in an hour. For our thermal subsystem, we account for the power consumption to be 0 simply because the power consumption of the bus heaters in the CubeSat is considered to be of such low orders of magnitude that we can consider it negligible. Tools we could use to optimize the specific measurements of power consumption from the powered components are voltmeters and some experimentation with resistors. Since power is equal to voltage squared over resistance, we can use voltmeters and varied resistances through which a current passes through in order to determine the power of an individual component when different subsystems are working in tandem or when one system is working individually and on its own.
The software states will vary depending on what the CubeSat needs to use. It will go through inputting power through solar panels, storing power in the battery, using the power to take pictures, and using the power to send pictures to the ground station. The program will also work through troubleshooting when there's a problem with power supply or communication.
For the software development, we are given a 1024 by 768 pixel image of the ocean and are tasked with detecting any plastic in the water. You see, our initial thoughts were focusing on what the average color of plastic is and finding any of those colors in the image. But then our thought process took a turn as we chose to completely eliminate the color of water from an image and focus on what we were left with. By doing so, we were left with multiple different particles in the ocean that we couldn't detect as plastic, or could be something that we don't actually need. Once we were able to eliminate the water from the image, the next step on our agenda would be to use edge detection to section off images that were floating in the water in order to eliminate the particles that could be reflections of the sun or other irrelevant items.
These two images provide a before and after of the use of the prototype code that has been developed to eliminate the color of the water. The picture on the left is the original image used for the test. The image on the right is a result of after the code was used to eliminate the water. In brief summary, this code finds the CSS3 color code name of the color of water and uses the imported modules PIL and web colors in order to produce the target image.
For the link budget, we need to find out how much data the Raspberry Pi's Bluetooth signal is able to transmit. We will need to factor in leaving a 3 decibel link margin to leave some leeway. The Shannon capacity, the limit for the amount of data that can be sent in the channel, will be calculated using this formula. When we are able to find the amount of power the CubeSat will be receiving, we will be able to calculate the final budget number. It will be more difficult for the CubeSat to transmit data when it is farther away from the ground station, so we will factor that into our calculations and planning as well.
The next section we would like to discuss is the data budget. 90% of the data budget will be sending down the images, but we also need things like the attitude of our satellite to make sure it is still working as intended. We found, on average, that our images are about 500 kilobytes each. In order to factor this data in, I did the math for 600 kilobyte images, so we have a little bit of headroom when sending all the necessary data down to us, as well as if the images are a little bit larger than expected. In one pass, or whenever the CubeSat passes over the ground station, it needs to send 5,760,000 bits of data. This means one image per pass and about 16 images per week. The frequency at which our CubeSat takes pictures will impact the amount of time it takes to downlink all of our data from one imaging session. For example, if we take one image every 10 seconds for 18 minutes, it will take 45 days to downlink all of our images and data.
To test our CubeSat, we're going to be looking at each of the various different systems that each individual member created and incorporate and test them together. For our thermal observation system, we will be heating the CubeSat to -10 degrees Celsius, 0 degrees Celsius, 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius, and 40 degrees Celsius. We will then measure the temperature at each of those points to confirm that the thermal observation system is accurate. To test our attitude determination and control system, we will be writing a calibration script to tell which direction the CubeSat is facing in correlation to the Earth. We're going to calibrate it and turn the CubeSat to face different directions and make sure that the calibration is working as intended. To test our communication system, we are going to send pictures from the Raspberry Pi to a computer at various different distances using various different pictures. With each of these, we're going to see how long it takes to communicate between the Raspberry Pi and the computer. To test our software system, we are going to run the CubeSat and make sure that each component is interacting with each other component the way that it's intended to. To test our power system, we're going to run the CubeSat in its different modes: science mode, downlink mode, and idle mode, to measure the power consumption over different periods of time. To test our imaging system, we're going to attach the CubeSat to a zip line, run it across a pool, and see if our imaging program takes pictures the way it's intended to. To test our structures system, we are going to measure the mass of each component and of the mass of the overall CubeSat to ensure that the CubeSat is light enough to function. We're going to test the durability of the structure by shaking the CubeSat and sliding it.
Thank you for watching. Bye!